Hello, this is Mrs. Poland for lesson 8.02, and we're going to work on the second example of chi-square goodness of fit. A traffic light is installed to allow traffic from a seldom used side street to cross a 4-lane highway. Because the side street doesn't get a lot of traffic, the light is set to provide a red light for the side street 80% of the time, a yellow light 5% of the time, and a green light 15% of the time. A resident who must pass through the light several times a day is suspicious that the light is not functioning according to the claimed distribution. He sets up a trail camera and programs it to snap a picture of the light at 200 randomly selected times throughout the day. Here are the results. Red, 173, yellow, 13, green, 14. Do these data provide convincing evidence that the light is not functioning according to the claimed distribution? First thing we know, there's no mention of confidence intervals. We know we're looking for convincing evidence, so we're going to use some sort of hypothesis test. We also have categorical data. We only have the frequency of the three categories of the light, red, yellow, and green. Since it's 3 categories and not 2, we can't do a 2 proportion test, so therefore we're going to compare the actual or observed frequencies counts to a known distribution of the 85% and 15% of the different colors. So the first thing we need to do is state the hypotheses. The null is the traffic light is functioning according to the claimed distribution. That's the 85% and 15%. The alternative is the traffic light is not functioning according to the claimed distribution. Next, we have to verify the conditions. The first two are similar to what we've used for all of our hypotheses procedures. We have a random sample as was stated, and the next thing we need to do, since we're not taking a snapshot of the same moment, we're taking 200 randomly selected times, we need to use the 10% condition and say it is reasonable to assume there are more than 200 times 10 or 2,000 times throughout the day to snap a picture of the traffic light. The third condition is very specific to all chi-square tests, and that's that the expected counts are greater than or equal to 5. It should be greater than or equal to 5. Now, I normally set up a table in order to do this. So the first thing you want to do is list out all the categories. We have 3 categories, and record the actual or observed counts. So 173, 13, and 14. And you should ensure that that adds to 200, which it does. The next thing you want to do is list out the expected counts. To get the expected, we know that you have a red light 80% of the time, a yellow light 5% of the time, and 15% of the time is green. To get the expected counts, multiply n times p. So 0.8 times 200 is equal to 160. 0.05 times 200 is equal to 10. 0.15 times 200 is equal to 30. You should add to make sure that it adds to the total count of 200. And so we can see that we met that condition. You now must name the test. So since conditions have been met, we can perform a chi-squared goodness of fit test, and you have to list the degrees of freedom. The degrees of freedom for specifically and only for a goodness of fit test is the number of categories minus 1. So in this case, we had 3 categories, red, yellow, and green, minus 1, and that's where I got the 2 degrees of freedom. This is something you do need to memorize. Next, we have to do our calculations. So if you go to the formula sheet, the chi-squared test statistic is chi-squared is equal to the summation of the observed minus the expected squared divided by the expected. So we can actually use the table we created. So the chi-squared is equal to 173 minus 160 squared divided by 60, divided by 160, plus 13 minus 10 squared over 10, plus the 14 minus 30 squared over 30. Now, we could calculate this by hand, but most of the time you're going to want to use the calculator, which I'll demonstrate in a minute. If you are using the calculator, you must minimum show the first and last term. You can't just list out one, you can't just list out none. You have to list the first and the last. Okay, so how do we enter this in the calculator? We go to a calculator page. This specific one, which is going to be different than the other chi-squared test, you're going to create a new, and make sure you always use a new document for this, otherwise you're going to run into a programming error. So O for observed, and let's list out the observed counts, which were 173, 13, oh no, and 14. And now I normally label the next thing E. And you're going to list out the 160, the 10, and the 30. We're going to add a calculator page. So control page, add a calculator page, and you're going to hit menu, statistics. It's a stat test, and option 7 for goodness of fit. With the drop-down menu, I list O for observed, E for expected, and the degrees of freedom which we calculated. And so here we get our test statistic, our p-value, our degrees of freedom, and something called the component list. So if I did want to find the value of each component, what you could do is hit vars, that lists the variable, and you see where it says stat component list. Sometimes that's really useful. You click it out and you hit enter. And so we can see the 3 values of our component, 1, 0.9, and 9. Okay, so 1.05, 1.06, 0.9, and 8.05. So you see like a really big difference in the last category, which was green. That added the most. So most likely there was a problem with the light when it was green. Okay, in any case, the chi-squared statistic ended up being 10.4896. We now want to calculate the p-value by hand, so you should always make a sketch. It's always right skewed. It's always positive, or not, rather non-negative. And so our chi-squared statistic was 10.4896, and we're going to shade appropriately. The probability that your chi-squared statistic is as great or greater than the test statistic of 10.4896, if we were calculating the p-value by hand, would be chi-squared CDF. The low would be 10.4896. The high would be 9E999. And the degrees of freedom would be 2. So that's low, high, and degrees of freedom. So let's go into our calculator and menu, statistics, distributions. That's where all the distributions are, and specifically the chi-squared CDF. That's 10.4896. The upper bound is 9E999. And finally, the degrees of freedom is 2. And we hit enter. And we see that the p-value is almost exactly the same as the p-value that was calculated in the hypothesis test feature of the calculator. Okay, so that was equal to 0.005275. Finally, we're going to draw our conclusion. So we see that our p-value is 0.005, which is certainly less than our alpha of 0.05. Remember, this is the p-value, and this is your significance test. So if your p-value is less than your significance test, you're going to reject your null hypothesis. Remember, getting this statistic, assuming that there's really no difference between the observed and the expected, there's a very small chance of that happening. This is 0.005 is very small. And so therefore, the assumption that there's no difference, okay, that the distribution, the expected distribution and what actually happens match, can't be correct. And so you would draw the following conclusion. Let me just erase this. Since the p-value is less than 0.05, we reject HO. We have convincing evidence that the traffic light is not functioning according to the claimed distribution. If you did want to go into it further and you were speaking to, I'm not quite sure who you would speak to when you have a problem with lights, but hopefully someone in the town, you would figure out which department it would be. You would say that the green light, there was a big difference between the actual and the observed. And you can see that 8.5 contributed a lot to that larger value of the statistic.